It is a well-known fact within Pentagon and industry circles that low-frequency radars operating in the VHF and UHF bands can detect and track low observable aircraft. It has generally been held that such radars can't guide a missile onto a target, i.e. generate a weapons quality track. But that is not exactly correct. There are ways to get around the problem according to some experts. Traditionally, guiding weapons with low-frequency radars has been limited by two factors. One factor is the width of the radar beam, while the second is the width of the radar pulse, but both limitations can be overcome with signal processing. The width of the beam is directly related to the design of the antenna, which is necessarily large because of the low frequencies involved. Early low-frequency radars such as the Soviet-built P-14 Tall King VHF band radars were enormous in size and used a semi-parabolic shape to limit the width of the beam. Later radars including the P-18 Spoon Rest used a Yagi-Yuta array which were lighter and somewhat smaller. But these early low-frequency radars had some serious limitations in determining the range and the precise direction of a contact. Furthermore, they could not determine altitude because the radar beams produced by these systems are several degrees wide in azimuth and tens of degrees wide in elevation. Another traditional limitation of VHF and UHF band radars is that their pulse width is long and they have a low pulse repetition frequency, which means such systems are poor at accurately determining range. As Mike Petrucca, a former Air Force electronic warfare officer who flew on the McDonnell Douglas F-4G Wild Weasel and Boeing F-15E Strike Eagle once described to me, a pulse width of 20 microseconds yields a pulse that is roughly 19,600 feet long. Range resolution is half the length of that pulse. That means that range can't be determined accurately within 10,000 feet. Furthermore, two targets near one another can't be distinguished as separate contacts. Signal processing partially solved the range resolution problem as early as the 1970s. The key is a process called frequency modulation on pulse, which is used to compress a radar pulse. The advantage of using pulse compression is that with a 20 microsecond pulse, the range resolution is reduced to around 180 feet or so. There are also several other techniques that can be used to compress a radar pulse, such as phase shift keying. Indeed, according to Petrucca, the technology for pulse compression is decades old and was taught to Air Force electronic warfare officers during the 1980s. The computer processing power required for this is negligible by current standards, Petrucca said. Engineers solved the problem of directional or azimuth resolution by using phased array radar designs, which dispensed with the need for a parabolic array. Unlike older mechanically scanned arrays, phased array radars steer their radar beams electronically. Such radars can generate multiple beams and can shape those beams for width, sweep rate and other characteristics. The necessary computing power to accomplish that task was available in the late 1970s for what eventually became the Navy's Aegis combat system found on the Ticonderoga-class cruisers and Arleigh Burke-class destroyers. An active electronically scanned array is better still, being even more precise. With a missile warhead large enough, the range resolution does not have to be precise. For example, the now antiquated Russian-made S-75 Dvina, known in NATO parlance as the SA-2 guideline, has a 400